Hello again. So in the previous recording, I went through in excruciating detail the process by which the capacitor gets charged. And the very, very short version of this was that the battery pulls positive charges from the top plate, deposits them on the bottom plate, but as the bottom plate gets more and more positively charged, it becomes more and more difficult. That is to say, we have to apply more and more force to put any more positive charge on the bottom plate. The difficulty, though, is we don't have any more force. The battery is supplying the force that it can supply through the electric field that it creates. So the force doesn't increase, and so what does increase is the repulsive force, trying to prevent any additional charges from making it onto the bottom plate. And eventually, the repulsive force from the charged bottom plate cancels out the force supplied by the electric field of the battery, at which point the net force is zero, the charging process stops, and in the middle, the flow is getting smaller and smaller and smaller. And so as the flow decreases, the light bulb, which is what this is here, gets dimmer and dimmer and dimmer because through a mechanism that I haven't yet explained, the brightness of the bulb is related to how much charge is flowing through the bulb every second. So that's an issue for a later lecture, why that's true and how that's related to all of this. My purpose now is to put equations to all of this. The calculation of the work that we have to do, or the energy that we end up storing, because those are equivalent, conservation of energy, right? The amount of energy you store has to be equal to the amount of work you did in order to charge the capacitor. The work that you did on the charges gets converted to stored electric potential energy. And the calculation of that is moderately complicated, and I'm going to go through it. And by moderately complicated, I mean it requires calculus. And I'm going to go ahead and do that. And if you happen to not be a calculus student, or you're not familiar with calculus, or you don't care about the calculus, then what I would say is listen quietly, try to understand what you can, try to get the sense of what I'm doing, even if you don't understand the mathematics particularly. And for those of you who do know calculus, hey, get to use your integral skills, your integration skills on a real problem. So we'll take a look at that, and I will point out for you algebra folks when the stuff that you need to the stuff you're responsible for, the concepts you're responsible for, when they start and when they end, and then when they start up again. Okay. Right. So remember that the energy of a charged particle is related to the potential energy of the electric field that we're moving that charged particle through. And the specific relationship is, so let's see, let W, capital W, equal the work, the total work that we do. My pens are running out of ink here. The total work done to, okay, I've got a bunch of bad pens here. Fully charge the capacitor. Okay, so capital W is the total work that we have to do in order to fully charge the capacitor. And I want to emphasize that capital W is the total work on all of the charges, and moving all of the charges, the total work combined, not simply the work done on one charge. Indeed, we don't really have an easy way of calculating the work done on a single charge. Not that we don't know how to do it. I mean, it's Q times V. But the problem is there are so flippin' many of these charges that we have no hope of calculating it by hand. So what we're going to do is imagine here that we have a huge number of charges, which is true, by the way. And by huge, I mean billions, tens of billions, hundreds of billions, trillions of individual charges. Okay, so we're not going to do them by hand, but what we're going to do, and now here comes this is the beginning of calculus. Okay, so again, for you algebra folks, try to follow the sense of what I'm doing if you don't understand the specific mathematics. What I'm going to do is think of the charge distribution. Remember surface charge density? Think of the charge distribution on the bottom plate as a continuous surface charge density, sigma. And I'm going to break, okay, now really here's where the calculus starts up. I'm going to break that total charge distribution into differential amounts of charge, dq. So rather than moving one single point charge, I'm going to move an infinitesimal. I'm going to imagine moving an infinitesimal amount of charge, dq. Okay? So let's calculate the work done to move a differential amount of charge. All right, so again, for you algebra folks, the word differential here, you can treat that as essentially equivalent to the word really, 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 really tiny, or the phrase really, really tiny. Differential charge dq. Amount of work required to do that. Since it's a differential amount of charge that we're moving, we're going to do a differential amount of work on that charge, or more specifically, sorry, let me be more careful. It is the electric field of the battery that is going to be doing the work on these charges. Okay. So, but I'm not looking at the electric field. I'm going to look at the electric potential difference of the battery. Okay. So. Okay, so take a look at, well, let me do it like this, actually. dq times v. Now, but I have to be careful here. I'm sorry, I misspoke a moment ago. The v here is not the potential of the battery. It's the potential of the electric field that's building up between the two plates. Okay, so v is going to depend on how much charge we have already moved. So maybe I better say this. Okay, where v is the V is potential difference across the plates. But I'll be more specific. Move out of the way here in a moment. All right, so here's what I want you to think about. Here's what I'm talking about. As we continue to charge the plate, more and more charge moves. More and more charge gets onto the bottom plate from the top plate. And what I want you to think about is some intermediate stage. It's well after we've started charging the capacitor, but long before we finish charging it. So we're at some middle point, some intermediate stage of the charging process. Okay. In which case we have moved some amount of charge that I will call little q, lowercase q. And I'm going to say capital Q to represent the total amount of charge that we eventually move when the entire charging process is done. Okay, so Q is the total charge moved. So the total amount of charge moved by the charging of the capacitor. But little q is the amount of charge moved at some intermediate point, some intermediate moment. Okay. The reason I'm being so careful about these definitions is because now I can say, since V is the potential difference due to the amount of charge that we've moved, and little q is the amount of charge that we have moved at some intermediate stage, then the amount of charge that we've moved and the potential difference is related through the capacitance of the capacitor. Specifically, this potential difference, which remember, this is not the potential of the battery, this is the potential caused by how much charge has been moved. That's going to be equal to the amount of charge we've moved so far divided by the capacitance. Remember, Q is equal to C times V, so I just solved for V here. Okay, so I have V is equal to this, and so now I'm going to replace V in this equation here with Q over C. Substituting. And so I have dW is equal to Q over C times V. Okay. I'm sorry. dQ times, sorry, I'm having a bad day, Q over C. So we had dQ, and then I'm replacing V with this, so dQ times this, okay. Or, and now I'm going to show you why I had a little trouble there, and you calculus folks have probably already spotted it. I will rewrite this in a trivial way. dW, I'm just going to reverse the order, Q over C dQ, okay? That is how much work you had to do to move a differential amount of charge through the electric field that already exists, I'm sorry, through the electric potential difference that exists up to this point due to how much charge you moved prior to moving this little bit of charge. Okay? The total amount of work is obtained, of course, by integrating this. Adding it all together. For you algebra students, integrating is a specialized kind of addition. And so this is the amount of work that we have to do to move one tiny little bit amount of charge. To calculate the total work done to move all of the charge, we have to add all these up. Okay? The mathematics is a little more complicated. It's not quite just a simple sum or addition. It's a little more complicated. It's calculus, but in any case, the answer looks like this in calculus. Okay, and the C, remember, is the capacitance, which is a constant. It's a property of the conductor. It's not going to depend. It has never depended, and it never will depend on what you do with the capacitor. So C, being a constant, can come out of the integral. And you know how to calculate that integral. Of course, that's about as simple as they come. And now, you algebra students, you can tune back in again. The answer turns out to be that the total work is equal to 1 over C 1/2 Q squared, or to put it the way we put it, the way any sensible person would write it, 1/2 Q squared over C, which is not actually the equation we use. This is perfectly correct, but we don't use this one, and the reason is we don't really have any way of knowing how many coulombs of charge we've transferred. So what we do is we be clever and we say, oh, I'm sorry, whoops. my mistake. Limits of integration. We're charging from 0 coulombs to a maximum of Q. So this actually becomes capital Q squared. I'm sorry. Okay. Yeah. Sorry about that. Right. Anyway, so this is a true statement, but it isn't useful. So I'm going to make it useful. By remembering what I said a moment ago, the total amount of charge that you can store is equal to C times V. And now, I apologize for this notation, but this really is the charge of the battery now. Okay, and it's okay because once I have fully charged the capacitor, the potential difference across the plates is, of course, equal to the potential of the battery. So whether you want, although I originally defined this as the potential difference across the plates, at the end of the charging process, it's going to be equal to the potential across the battery. And so as a practical matter, we just think of it as the potential difference applied by the battery. Anyway, so then I replace this. And so I find that the work is equal to 1/2, okay, Q squared is CV quantity squared over C. And here's my final answer, 1/2 CV squared. And that is the answer. That's how much that's how much work you store in the capacitor when you charge it fully. V is the potential difference applied by the battery or whatever your potential source is. C is the capacitance of the capacitor. That's a known quantity. It's stamped on every capacitor. And then you just plug this in. And notice that these things are, this is an easy thing to calculate because you control what battery you attach to your circuit. You can see what the capacitance is. As I said, it's stamped on the capacitor. And so this calculation is trivial. So that's the answer to the question. And for our example here, we had a 1 farad capacitor. We attached a 3-volt battery supply to it. And so we stored 1/2 CV squared, 1/2 1 farad times 3 volts squared is 4.5. 3 squared is 9, divided by 2, 4.5 joules of energy. When I did that thing with the light bulb, I stored 4.5 joules of energy. Okay. Easy. Or at least it would be easy if there weren't one additional complicating factor. And that is, in this calculation, I ignored the light bulb. And that turns out to be an error. We have to take into account the light bulb. And the reason for that, I'll give you a taste of why, that the light bulb gives off light, which is a form of energy. And that energy had to have come from either the battery or from the capacitor or whatever. Okay, so but that's energy that we lost because it got radiated out in space and into our eyes and so on. We haven't taken that into account. Okay, so our next task then is to figure out how we have to handle the light bulb. And the answer is going to be that the light bulb has its own electrical property, and that electrical property is called resistance. And we're going to, in the next few lectures, we're going to find out what resistance is, where it comes from, how you calculate it, and then finally, how we wind it into this calculation to improve this. Okay, so that's something to look forward to. Yeah, I think we're done with capacitor for now.